Hi, I'm recording. Okay, I'm gonna get all artistic on you. Woo! I'm going to explain sodium-potassium pumps, action potentials, calcium, and muscles, and how all three affect your actin and myosin, and how they bind. And I looked this up in my physio notes, and they got spilled on, so it was kind of fuzzy, so I'm trying to do this from memory, and I'm finally getting around to doing it. Hopefully this sounds right and I don't screw you up some more. Anyway, so you're resting. What if I just put this here? Okay. Your resting membrane potential is going to be negative 70 millivolts. Great. So what the resting membrane potential is the potential energy for you to have something happen, a thought or an action. And it's that way because it's like a coiled spring. There's the balance on either end of the membrane. You have lots of sodium. We're going to make sodium red. Let's see. Sodium is red. They're circles. We're going to make potassium. We're going to make it green, triangles. Anyway, so they're all positive, but you have more potassium on the inside than you do on the outside, and more sodium on the outside than you do on the inside. So sodium naturally wants to diffuse from high to low, and potassium naturally wants to diffuse from high to low, but they can't because they're being blocked by this membrane. So what you have to do to get them across, to create that negative 70, is you have these pumps. And this sodium-potassium pump is a form of active transport, and you need energy, so we're going to use ATP. So ATP comes along, and it's going to stick a phosphate, boink, which is negative, but it's going to stick a phosphate onto this pump, which is going to activate it, so that way 3 sodiums, they're going to bind in there, and that is going to cause the pump to change shape, and it's going to flip. So it's flipped, and now those 3 sodiums are going to go out. So the 3 sodiums went out, and they're going to naturally want to go in because you've got more sodium out here than you do in there, but they are not able to because as soon as that happens, now it is changed shape. So now only the potassium can fit in, and woohoo! So then I have 2 potassium, and they fit in there into this activated pump, and that causes the pump to change shape again, and it dumps them out. Bunk. Now I have 2 potassium out here, and I have 3 sodium up there. So overall, I have a net charge of +1, because if this is my membrane potential, I've got 3 sodiums, and I have 2 potassiums, so that makes it more positive outside, and it makes it more negative inside. Even though they're both positive ions or anions or whatever they are, it's more negative on the inside. And given the chance, they're going to want to follow their concentration gradient, so all of these sodium out here are going to want to go in, and the only way that they can go into the inside of the cell is if a gate opens. So when a gate opens, all the sodium come in here, and that is called depolarizing because it goes towards 0. So you're at negative 70, and that's the potential for the sodium to come in. When the sodium come in, that equals depolarizing towards 0. When it gets to positive 30, then it stops, and then you get a refractory period, and then it repolarizes back to negative 70. And the way that that comes into play with your action potential, I'm going to draw a neuron here. Boink, 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 boink. This is a neuron, I'm going to focus right here. Oh, I'm looking through my phone. Right there. I'm going to focus on the axon terminal of the neuron and the motor end plate of the muscle. So the action potential is all this sodium coming in. All the sodium comes in, opens the gate. It creates like a shock wave. So this depolarizes it enough to open this gate, depolarizes it enough to open this gate. And eventually you get down here, use a different color, and I have calcium comes in. So these are calcium gates, and the calcium comes in. What the calcium's job is to do is there are vesicles of your neurotransmitter, and this neurotransmitter is acetylcholine. So calcium is going to bind with this little doohickey over here called a synaptotagmin, and it's going to form a snare protein with the calcium. Hey, Peach. Going to form a snare protein, and that is going to allow the acetylcholine to exocytose into the synaptic cleft. Now I have all of this sodium in the synaptic cleft. Acetylcholine. I have all this acetylcholine in the synaptic cleft. What the acetylcholine does is it goes to these gates, and these are acetylcholine nicotinic ligand gated channels, and that means that the acetylcholine has to bind two of them to each end of this gate, and then that gate will open. When that gate opens, this sodium that we had talked about earlier has a heyday, and they're like, woo, we can all diffuse in. So now the sodium is diffusing in, sodium's diffusing in, and this gets depolarized, it becomes more positive, goes to negative 30 or positive 30. When it gets to positive 30 and it wants to stop, the gate's shut. And what do you do with all this acetylcholine that's out here? You have an enzyme called acetylcholine esterase comes, and that takes care of it. So in the meantime, your sodium has another domino effect, shockwave. Oh, she does want to help. Shockwave effect. So more sodium comes in, all the way in, until you get to the T-tubule of the muscle. Now this is skeletal muscle. It's different between skeletal and cardiac, but for skeletal muscle, you have something here called ryanodin, and it's basically a little bridge, and it allows for the positive potential, I guess, to come into the muscle's sarcoplasmic reticulum. The muscle sarcoplasmic reticulum stores calcium, and it comes in, it opens the gates, and calcium leaves sarcoplasmic reticulum. Yay! And it goes all over the cell. Yay, Peach! When you have calcium all over the cell, then that goes to your actin and myosin. I drew something. Oh, here it is. This is a sarcomere of your filaments. This thick one's going to be the myosin. This is going to be the actin, so recognize it's green, and I'm going to make the actin red. When they contract, they pull together. They shorten. The muscles don't shorten, the filaments in there do with the actin myosin. But they can't without calcium. What calcium does is calcium comes in, and this is actin. Actin has these binding sites for myosin, but they're all covered up right here with tropomyosin. Tropomyosin has these receptors called troponin, so calcium comes, binds to troponin, and it literally lifts the troponin off, or the tropomyosin off of the actin. So now these binding sites right here are available for my myosin. I'm going to draw new actin. Okay, this is my myosin head. It is polar, so this head is slightly negative, or slightly positive, and this is slightly negative, so that keeps it in that cocked bound position. Because it's positive, it can attract ATP. So ATP comes and it goes into the myosin head. And the myosin head is a kinase, which is a protein that does things. So it's going to break the ATP into ADP plus a phosphate. At the same time, when the ATP, because it's so negative, it's going to force this myosin head to cock back. And when it cocks back, it binds to the binding site right here. At the same time, the kinase has turned ADP and phosphate, and it spits the phosphate off. So the phosphate is out. And so this is ADP right here. Spit the phosphate off. Because it spit the phosphate off, now it's the negative and negative, but it's not so repulsive that it allows for the myosin head to do what is called a power stroke, and it pulls the myosin along with it because it's attached. So it did a power stroke. Now it's back into its original conformation, and the phosphate was already out, but now the ADP is out too, and so it's stuck here. And the only way that it can be released and go back into its dropped position, so now I'm no longer, I guess I'll draw that it's attached. So it's attached. The only way that it can, no more doodads either, no more ATPs. The only way that it can drop down is if another ATP comes along to release it. Now you're back to step 1, and you need another ATP to come in here to cock the head back so it can grab, spits out the phosphate, does the power stroke. Now you're stuck on here, it needs another ATP to drop it down, and you're back to step 1. And that's why when you have rigor mortis, if you run out of ATP with your glycolysis, and that's why you get really stiff muscles, because there's no ATP to release the myosin from the actin. And that was 12 minutes. I hope that was helpful at all. Oh, this is the part where I say, you can subscribe to my channel, and I do videos every Wednesday. My next video is going to be about my cat. Where'd she go? Okay, well, thanks for watching. Subscribe and shit.